An AC motor operates because of the interaction between the magnetic fields of its rotor and its stator. In most AC motors, alternating current is supplied to the stator windings. The current flow causes the magnetic fields around the stator windings to increase, decrease, and change polarity. Let's look at an example to see how the magnetic fields of the rotor and the stator interact in a simple AC motor. These two coils of wire make up the stator. This bar magnet is the rotor. It has a north pole and a south pole. When current flows through the stator coils, magnetic fields are created around the coils. Each magnetic field has a north pole and a south pole. In our example, we're starting with the north pole of the rotor next to a stator north pole and the south pole of the rotor next to a stator south pole. The like poles repel each other, so the rotor starts to rotate. As it does, its momentum and the attraction of its poles to the unlike stator poles help the rotation to continue. When the alternating current flowing through the stator coils reverses direction, the stator poles reverse. As a result, the like poles are next to each other again. The like poles repel each other, and the rotor continues to turn. This sequence will continue as long as the stator windings are being supplied with alternating current. A three-phase AC motor is more complicated than the example we just saw, but the basic principle of operation is the same. The interaction between the magnetic fields of the rotor and the stator cause the rotor to turn. This illustration represents the stator of one type of three-phase AC motor. This stator has 6 coils. There are 2 coils, or one coil pair, for each phase of alternating current. The coils are connected through a common point in what is called a Y connection, or a star connection. In this arrangement, the coil pairs for each phase are 120 degrees apart from each other. As alternating current flows through each coil pair, magnetic fields are created just like they were for the simple AC motor we looked at earlier. However, since there are 3 coil pairs, the stator always has 3 north poles and 3 south poles. As current flow through each coil pair increases, decreases, and changes direction, each magnetic field increases, decreases, and changes polarity. Because the coil pairs are 120 degrees apart from each other, the net effect through the complete three-phase cycle is that the overall magnetic field between the stator coils rotates. The rotor in this type of three-phase motor is an electromagnet. Its magnetic field interacts with the stator's rotating magnetic field, and as a result, the rotor turns. In this topic, we discussed electric motors. We learned about basic motor operation, and we discussed DC motor operation and AC motor operation. Now try some practice questions to check what you've learned. This is a very simple example of an electric motor. It consists of 2 bar magnets and a rotor. The rotor is the part of the motor that moves or rotates. The 2 bar magnets which do not move are called the stator. Now let's take a look at how the commutator, brushes, and rotor windings cause a DC motor to work. This horseshoe magnet is the motor's stator. The north and south poles are indicated by the letters N and S. The poles of the rotor are indicated in a similar way. When the rotor is in this position, the north pole of the rotor is repelled by the north pole of the stator and attracted by the south pole of the stator. Similarly, the south pole of the rotor is repelled by the south pole of the stator and attracted by the north pole. The combined effect of these attractions and repulsions moves the rotor. At this point, the commutator and brushes switch the direction of current flow through the rotor coil. The change in current flow direction switches the polarity of the rotor. This change in polarity keeps the rotor rotating in the same direction. It continually moves toward opposite poles. The rotor in this type of three-phase motor is an electromagnet. Its magnetic field interacts with the stator's rotating magnetic field, and as a result, the rotor turns.